Alright guys, so we are going to look at Young's modulus. Part 1. Young's modulus is a parameter that defines the stiffness of materials and their ability to withstand deformation under stress. To understand Young's modulus, we need to first define a few key terms. Number 1. Tensile stress, represented with sigma. This is the force applied per unit area of a material. Mathematically, it is expressed as sigma equals to F over A. Where sigma is the tensile stress in pascals or Newton per meter squared. F is the force applied in newtons, and A is the cross-sectional area in meter squared. Tensile stress tells us how much force is being applied to a specific area. Let's think of it this way. If you pull on a thick rope, the stress is lower. That is because force spread over a large area. But then if you pull on a thin rope with the same force, the stress is higher. This is because the force is concentrated on small area. The thin rope is more likely to break because the stress is higher. Then 2. Tensile strain, represented with epsilon. This is the change in length per unit original length of a material under stress. Mathematically, it is expressed as epsilon equals to change in L over original length LO, but change in length is the same as extension. Therefore, strain equals to extension over original length. Let's define the terms. Epsilon is a tensile strain. It has no unit because it's a ratio of lengths. Then E is the extension in meters. LO is original length also in meters. Strain can be expressed as a decimal, example 0.01, a percentage, example 1%, or a ratio, example 1 over 100. Tensile strain tells us the percentage by which a material has stretched or compressed. Now let's define Young's modulus. Young's modulus is the ratio of tensile stress to tensile strain. It is a measure of how stiff a material is. Let's think of it this way. A material with high Young's modulus is very stiff, like steel. It doesn't stretch much. A material with low Young's modulus is flexible, like rubber. It stretches easily. Mathematically, so Young's modulus E equals to tensile stress over tensile strain in terms of symbol sigma over epsilon. But we know tensile stress is force over area, then tensile strain is extension over original length. So we substitute them in, and then we simplify, and we get Young's modulus to be equal to FLO over AE. The unit of Young's modulus is Pascal or Newton per meter squared. Let's define the terms. So E is Young's modulus in Pascal or Newton per meter square. We've already said that. And F is the force applied in Newton. A is the cross-sectional area in meter square. LO is the original length in meter. And the E is the extension also in meter. Why is Young's modulus better than Spring's constant? Now, spring constant K depends on the size of the spring. That is, a thick spring has higher spring constant than a thin spring. Also, a long spring has lower spring constant than a short spring. But then Young's modulus E depends only on the material. For instance, all steel has the same Young's modulus, regardless of size. This allows us to compare materials fairly. Key insight into this. Young's modulus tells us about the material itself, not the object. A thick steel rod and a thin steel rod have the same Young's modulus, but they have different spring constants. This is why Young's modulus is better for comparing materials. Let's look at Young's modulus of common materials. So the table here shows Young's modulus of some common materials. Now, in the table we have the materials, their respective Young's modulus, and then also their classification. Now you see that the unit of Young modulus here is gigapascal, meaning all the values here are multiplied by 10 to the power 9. So if we take the first material, diamond, it is having Young's modulus of 1200 gigapascal. Now this is a huge value, and therefore diamond is classified as an extremely stiff material. The next one, carbon steel, having Young's modulus of 207 gigapascal. This is also huge. So carbon is classified as a very stiff material. Then copper 130 gigapascal. That's somehow huge. So copper is a stiff material. Aluminium is 69 gigapascal. That's moderately stiff. Glass has strength modulus between 60 to 70 gigapascal. That is also moderately stiff. Then wood or oak has Young's modulus between 10 to 12 gigapascal. That's somehow low, so it is flexible. Plastic or nylon 1.5 to 3 gigapascal. That is quite low, so it's very flexible. And then rubber 0.1 gigapascal is very low, so rubber is extremely flexible. End of lesson. Subscribe, comment, and like. Thank you.